Okay, hello everybody. We're recording this lecture over the November 1st weekend because we have very little school, so here we go. This is the beginning of our new unit in Precalc C, and this unit is sequences. Okay, so this is going to be a very, I think, kind of interesting and exciting. This is completely different from every single other thing we have done in all of Precalc A and B and in Precalc C up to this point. Unlike all the mathematics that we've been studying since we got to high school, which is essentially the study of continuous functions, now we are going to look at kind of discrete mathematics. Maybe you know something about this before. One interesting thing about this unit is sort of almost kind of all of it is sort of just common sense or something like that. Okay, I want to assume that you have any experience with this. So let's just start with some simple kind of ideas. So this will just sort of give you a taste of the unit. Well, there's this famous story which is just false. There is this mathematician named Gauss. He is probably one of the 3 greatest mathematicians of all time or something like that. This is the person who invented Gaussian elimination, although actually that was done, thousands of years earlier by various Chinese mathematicians. But anyway, Gaussian elimination was named after Gauss. A lot of things are. So there's this story of him, which once again is not true, but he's 8 years old or something like that, and he is very, very smart, and therefore being kind of annoying and acting out in his class in Germany, and his teacher says to Gauss, go off in the corner and add up all the numbers from 1 to 100, thinking that the teacher would keep him busy, and then he pauses for basically like 1 second and gives an answer. So how did he do such a thing? How can you just add up all the numbers from 1 to 100, so quickly as opposed to actually calculating them? Well, the idea is something like this. We say, alright, I want to add 1 plus 2 plus 3 plus, and we go all the way up to 100. So I'll just say plus 99 plus 100. So this is what I want to know, right? What is the sum from 1 to 100? Well, now if I kind of write it out like this, and also introduce a little bit of algebra, so in other words, let big S be this sum that I want. Now we perform this brilliant move, which is to kind of repeat the sequence, fold the sequence in half. Okay, well, folding in half works really well if there are an even number of terms, like there are now, but more generally, we can just kind of write the entire thing backwards. Alright, if you've never seen this before, this is really kind of brilliant move. Just take the entire sum, the sum of the numbers from 1 to 100, and write them backwards. So I've just done that now. So what? Well, the so what is, if we then go and add these numbers, what do we get? Well, 1 and 100 is 101. 2 and 99 is also 101. 3 and 98 is also 101, etc. And in fact, that's not just a coincidence. We're always going to have in any given column a sum of 101 because these numbers are going up by 1 and these numbers are going down by 1 each time, and so their sum is remaining constant. And so we get over here, so it's 101, and well, what happens, of course, when I add these 2 equations, when I end up with this twice the thing that I wanted. And then we just kind of remark that how many of these 101s do I have? Well, there are 100 numbers, so there were 100 columns, so there's sort of like 100 of these or something. And well, there it is. I've just determined that 100 times 101 is twice the number I was looking for. And so what is the number I was looking for? It's just, that over 2. So 50 times 101, and I guess that's just like, make sure not to mess this up. That's right. That's 5. Why have I'm suddenly doubting myself? No, 50 times 100 is 5,000. Yeah, it just is. So that's 5,000 and then an extra 50. So 5,050 is in fact the answer, and it's the kind of thing where if you've thought about this before, or even just thought about it kind of on the spot, then you could be able to give that answer, you know, almost instantly. Well, is this method kind of generalizable in some kind of way? I think it really is. And so let's just come up with a formula now. There was nothing special about the numbers from 1 to 100. Let's come up with a formula for the number of the sum of all the numbers, you know, up to some kind of point. So let's say n. Yeah. So I get, here we have, you know, n minus 1, and then finally n. Okay, so what is this? I'm just going to call it s, but it's really the sum of all the numbers from 1 to n. And how should I do this? Well, the exact same way, right? We just write the entire sequence again backwards. So this becomes n. Here we have n minus 1. Here we have n minus 2, etc. Plus, and I just throw in some dots, and then this is 2 and then 1. So this is simply just writing the entire sum backwards. And then, just as before, I add this sequence, and okay, well, what do I get? Well, 1 and n is n plus 1. So I'll put, so that's n plus 1. What happens when I add 2 and n minus 1? Well, that's again n plus 1. If I had 3 and n minus 2, that's also n plus 1. Okay, and now come these kind of mysterious, you know, dots. Okay, more on that in a second. But should I kind of trust these dots? Well, I suppose so, because after all, just as before, these numbers are going up by 1. These numbers are going down by 1, and so if the first row is going up by 1, the bottom row is going down by 1 each time, then the any particular column is going to be constant, I suppose. Anyway, skipping over to the end here, this is also n plus 1, and this is also n plus 1, and when I add, I get twice the thing that I wanted. And now the question is, how many of these n plus 1s do I have? And the answer is I have n of them. What have I just determined? I've just determined that n times n plus 1 must be twice the thing I was looking for. And so the answer is that s is n plus 1 over 2. Alright, this is kind of incredible. Let's pause for a second to kind of remark or something on this. That well, this is just a great formula, right? This is kind of formula that every person should know. Every high school math student should be aware of this formula and understand how to derive it, and it's quite useful. So if we want to be a little bit more maybe specific, we can call this, you know, S sub n or something like that, because it's a formula which says, you know, tell me how far out you want to go, and I'll tell you the sum of all the numbers from 1 up to that point. Okay, cool. Two more things to say. One is a little bit maybe vague and kind of philosophical, and doesn't work so much if we're doing this on video. But what I would, if we were live, I would sort of ask the room, you know, do you trust this proof? In particular, things get a little kind of weird here with these, you know, dots. What's up with these? What's up with these dots? You know, that's really something that we don't typically like in a math proof. You know, you're doing some kind of very, very careful math proof, and then you just sort of say, well, you know, and so on, or something like that. If you were signing some kind of contract with someone about, you know, the precise rules for how you were going to get paid for some work you were going to do, or, you know, some kind of business contract or whatever, and, you know, then they got to page 3, and then there was just pages 3 through 50 were just like, you know, said ... you know, etc. Don't worry about it too much. Then you might suddenly start to get worried. So I would like to sort of, on the one hand, I would like to encourage you to think of this as a quite good argument. Perhaps we want to classify this as a discovery of the formula, but perhaps we should have some doubt about whether this constitutes a proof of this formula. And okay, so put it in the back of your mind for 2 weeks or something, that maybe there's some kind of better method here for establishing some fact like this that's a little bit more careful and avoids this kind of and so on reasoning that we've seen. Alright, the other thing I want to say is a little bit more of a positive thing, that there's a proof of this that is sort of more geometric in nature, kind of more beautiful and intuitive. And that is, well, suppose I want to come up with, suppose I want to take the numbers from, well, say 1 to 4. So I want to add the numbers 1 to 4. So, okay, well, I take, 1 and 2 and 3, and I'm going to write these numbers in this kind of beautiful little triangular formation here. And, well, that triangle represents the sum of the numbers from 1 to 4. And then, what is the sum of the numbers from 1 to 4? I'll just call this, let's see, I'll call this n over here, where n in this case is 4, but the argument should work for anything. And now, ultimately, what did I do over here with this algebra? I sort of produced another copy of that sum, but sort of in a different orientation, with the numbers reversed. Well, now I can do that same thing, right? This is sort of calling out to be complemented with another copy of the sum of the numbers from 1 to 4. And, well, there's this kind of blue triangle, which is the sum of the numbers from 1 to 4. And there is this black triangle, which is also the sum of the numbers from 1 to 4. And but based on the way I've sort of put them together, what in fact is formed is a rectangle. And so this is the visual proof of this exact same fact, right? That if you want the sum of the numbers from 1 to 4, what you should really do is construct the rectangle whose dimensions are n by n plus 1, and then divide by 2, owing to the fact that the thing we want is actually sort of half of that rectangle. Okay, so that's kind of nice. And this sort of argument over here gives rise to this thing called a triangular number. What is a triangular number? A triangular number is any number which is the sum of the numbers from 1 up to that point. And so what are the triangular numbers? Well, the first triangular number is 1. The next triangular number is 3. The next triangular number is 6. And the next triangular number is 10. And there's even kind of a notation for this, and the notation is to use t. So this is like t1 is 1, t2 is 3, t3 is 6, and t4 is 10. So okay, great. This was just a sort of an introduction and kind of taste of this whole unit. Okay, pause for a second and kind of erase all of this, and alright, well, I wrote on the top of the board, Introduction to Sequences, so, oh, okay, well, I'll just keep going. And so, well, what is a sequence, is a good question. Well, it's kind of like a list, right? And so, what is a sequence? I'll just give a kind of a weak definition right now. A sequence is an infinite list. An infinite list. Okay, well, that's kind of vague. Let's just give an example. So what's an example of a sequence? Okay, here's one. How about, like, 3, 5, 7, well, something like this. And, well, this is the kind of thing that you find on, like, intelligence tests or something like that, IQ tests, hey, complete the pattern. But these problems are all just sort of bogus because, well, who knows what the pattern is, right? So what's one way in which this sequence could continue? Well, one option is perhaps that these were just the odd numbers. So if these were the odd numbers, then if I were to sort of prompt you right now with, finish the sequence or continue the sequence, then you might say something like, well, it's 3, 5, 7, 9, 11, 13, 15, etc. Just make sure we're good here. Yeah. But of course that might not be the sequence, right? Perhaps the sequence was instead the sequence of odd primes. Well, if this were the sequence of odd primes, then this would be 3, 5, 7. Then we wouldn't go to 9, right? We would go to 11, 13, 17. But the sequence could also just be like, freaking anything, right? 3, 5, and then 7, and then who knows what could come next? 8, 1, 1, 1, something like that. So there's actually no way to predict what sequence someone is talking about by just throwing in some dots, the kind of dots strike again or something like that. So all right, it's just not reasonable to live like this, right? With just dots substituting for an explanation, and so we have some kind of notation. What's our notation? Just sorry for those computer science freaks out there, but we are going to start counting from 1. That's just how everybody does it, so just get over it. So if we want to describe this sequence more carefully, we might say something like, A1 is 3, which is to say the first term of this sequence is 3. What's the second term of this sequence is 5. What? And the third term of this sequence is 7, something like that. What the fuck are you talking about? Alright, Siri seems to think I am talking to him, her, whatever. That's completely obnoxious and outrageous. Alright, whew. Okay, good. Well, using this kind of notation, perhaps I can bring more clarity to this discussion of sequences by using this notation to actually define my sequences properly. And so one thing we can do is, let's take a famous sequence. So the Fibonacci sequence, for example. Never remember how to spell this guy's name. Fibonacci sequence. Okay, this is some sort of like 12th century Italian mathematician named Fibonacci who did a lot of investigations with this kind of branch of discrete math, and you've probably seen this sequence before. We're going to learn actually more about it later, including the sort of history of how it got started. But for now, I'll just tell you what it is. It's this thing, right, where we go like, 1, 1, and then we add the 2 previous terms. So that's 2, we add the 2 previous 3, add the 2 previous 5, add the 2 previous 8, add the 2 previous, 13, 21, 34, etc. Okay, well, suppose I want to communicate the Fibonacci sequence to someone else who's never heard of it before. There is a way. And the way is not with ... but with some kind of precise algebraic explanation. So, for example, I can tell you that the first term of the sequence is 1, that's just a stipulation. The second term of the sequence is also 1. But for subsequent terms of the sequence, and I hereby define the sequence recursively, and this is supposed to apply if n is greater than 2, well, the nth term of the Fibonacci sequence is, in fact, by definition, computed as the sum of the 2 previous terms. And so we can say something like a n minus 1 plus a n minus 2. And so here we have a recursive definition of the Fibonacci sequence. So, and now this is completely precise, and there's no sort of a room for misunderstanding the ... Okay, so that was our introduction to sequences. The rest of this video is going to be devoted to a very particular kind of sequence, and it's basically the easiest kind of sequence that there is. So it's just usually the one that we learn first. You may have even seen this kind of thing in middle school or whatever, or it may just seem familiar to you because it's just all kind of common sense. So that is arithmetic sequences. Okay, what are arithmetic sequences? First I'll just start with an example. My paper. I'll start with an example. Here's an example. 5, 8, 11, 14, 17, etc. Okay, what is the key feature of this arithmetic sequence? The key feature is that we increase by some sort of constant every single time. So we're going up by 3, up by 3, up by 3, up by 3, etc. Okay, so that's kind of nice. And well, there are two ways. I sort of advertised that we would like to kind of move away from this dot dot dot. So how could I communicate this sequence to someone else? Well, I think I have two sort of options. I can communicate this sequence recursively. And I can communicate this sequence explicitly. Okay, what do I mean by that? Well, suppose this was your sequence that you had in your mind and you wanted to explain it to somebody else. How would you do that? Well, one thing you sort of must say is what the first term of the sequence is. So okay, you can say, all right, well look, everybody, the first term of my sequence is 5. And, you know, here's how you get a term. Well, you just add 3 to the previous term. It's a very honest kind of way of talking about this sequence that we've made up here. And so here it is. For n, for a sub 1, the first term, the answer the value is 5. But for the nth term, for n greater than 1, so for subsequent terms, you just add 3 to the previous term. Okay, this is called a recursive definition of the sequence, and this person's looking a little evil, and this is perfectly legitimate. But it is also possible to give an explicit introduction to this sequence. You can just give me, and what does that mean? It means that I can just give a formula for the nth term of the sequence in terms of n. And well, how should we think about this? Well, the first term is 5. Okay, great. What's the next term? Well, the next term is 5 plus 3. Okay, what's the next term? The next term is 5 plus 3 plus 3. The next one is 5 plus 3 plus 3 plus 3. The next one is 5 plus 3 plus 3 plus 3 plus 3. And so actually every single term in an arithmetic sequence is really just going to be 5 plus a bunch of 3's. So, okay, let's make sure, kind of be careful and get this right or whatever. If I'm on the second term, how many 3's have I added? 1. If I'm on the third term, how many 3's have I added? 2. If I'm on the fourth term, how many 3's have I added? 3. And so the answer is that to get the nth term in an arithmetic sequence, I need to add 3 n minus 1 times. Okay, so I think that's pretty straightforward. And okay, to introduce some kind of a vocab here or something, I can give a precise definition of an arithmetic sequence. And I'll just do that now. An arithmetic sequence is a sequence such that the differences, I don't believe I'm writing this down, but the differences between a term and the previous term is constant. Between a term and the previous term is constant. Okay, so what does that mean? What in this case is that constant? The answer is 3. So this sequence, according to this definition, this sequence is arithmetic because the difference between 8 and 5 is 3. The difference between 11 and 8 is 3. The gap between a term and the previous term. The difference between 14 and 11 is 3. And so we call this the common difference. So the common difference in an arithmetic sequence is just this number d, which is how much we increase by each time. And so what does a generic arithmetic sequence therefore look like? Well, the first term is going to be a. Let's just say. Okay, and then what's the next term look like? A plus d. The next term, a plus 2d. The next term, a plus 3d, etc. Okay, and if that's what a generic arithmetic sequence looks like, then what is the formula for the nth term? Well, I think it's pretty clear. It's just a kind of more general version of what we already did. The explicit formula for the nth term in an arithmetic sequence with at first term a and common difference d is, well, every single one of these terms is going to be of the form a plus a bunch of d's. How many d's? Well, it's always going to be that by the time I'm on the nth term, I've added d n minus 1 times. So this is sort of a formula, but it's kind of obviously the correct formula that will tell you what the nth term of an arithmetic sequence is. If you tell me what the first term is, and you tell me what the common difference is. Okay, great. There's pretty much just like one more big thing to do, and then we're good. So what I want now is, oftentimes I want to sum the terms of an arithmetic sequence. Okay, so I want to know what happens when you just add them all up. Okay, so this is what I want right now, and in class I would kind of give you guys all a bunch of time for this, so it's a little bit sad that we're not going to be doing that. Is this a better marker? I don't know. So what I want right now, so goal, I'll just write this up here. Goal, find a formula for the sum of the first n terms of an arithmetic sequence. Okay. This is our goal. Alright. This is perhaps not obvious, kind of what I'm talking about, but I have a generic arithmetic sequence, and I want to know what happens when you add up, say, the first 15 terms of this sequence. What do you get? Okay. So let's, well, I could give you some time to kind of dwell on this or something and think about it. But maybe we should instead just kind of start, right? What am I talking about? Well, suppose I take a generic arithmetic sequence, which, as we've said, has first term a and common difference d. Then ultimately what I'm asking is, okay, you have this sort of term a, and then what's the next term? Well, the next term is going to be a plus d. And what's the next term? Well, a plus 2d, and I'm going to do this for a while. How long? Well, I want to keep adding terms until I get to the nth term, because I want to find a formula for the sum of the first n terms of an arithmetic sequence. So what is the form of the nth term of a generic arithmetic sequence? Well, as we just said, when we get to the nth term, then by that point we've added d n minus 1 times. So this right here is, let's not forget, this is the nth term, otherwise known as a sub n. Okay, and what is this? I want to know what this sum is. So in fact, let's agree to call this s sub n. So the subscript says that this is supposed to S for sum, so this is supposed to be the sum of the first n terms. Okay, so, well, now that I know what I want to do, maybe it's a little bit more clear sort of what's going on. And when someone says find a formula for, that's always maybe a little bit vague. What do we mean when we say find a formula for? Well, isn't this a formula right here? Haven't I kind of written something out? Well, the thing is there's this kind of dot in here, right? So this is really not a formula at all. This is sort of just a definition for S of m. So you can think of this task, find a formula, as get rid of this dot dot dot. Collapse this whole thing into some kind of formula. And well, what is that formula going to include? So now let's mention that. So in terms of what? What sort of parameters or inputs are going to be in this formula? Well, you certainly need to give me A, and you need to give me D. So once you tell me the first term and the common difference, that defines the arithmetic sequence. And then you also need to tell me what n is, because after all, we're being asked to add up the first n terms. Alright, so now I think I have a better sense of what's going on. Just going to grab a new marker. Seems like a good time for that. So, goal, find a formula in terms of A, D, and N, which represents the entire left-hand side of this thing. Okay, well, I'll put a line here, because that's kind of the task. How are we going to do it? Well, alright, in a perfect world, I would put you'd all be in class live, in groups or whatever. You'd try and you'd mess around and you'd figure some things out. Some people would get it, they'd explain it to others. But, well, here we are, Zoom school. Let's just go for it. The answer to this is you just do the Gauss thing. So you just do the Gauss thing from the intro. This is at least one way to do it. So here we go. We use the Gauss method. And what do I mean by that? Well, let's just take the thing. So I'll rewrite this now, right? This is A plus D plus A plus 2D plus, and maybe I'll even try to add in, two more terms here. So the last, this is all S sub n. Maybe there's not enough space, but maybe there is. What do the last two terms look like? Well, by the time I've got to the nth term, that's of the form A plus n minus 1d, as we've said. Remember, the goal is to add up the first n terms. So that's the nth term, and the previous term, I've now added d even one less time. So that's n minus 2d. Okay, so let's just to clarify, this is A sub n, this is A sub n minus 1, etc. Okay, so now comes the moment where I'm going to finally kind of do something, and the do something is to just write this entire thing backwards. Okay, so here we write A plus n minus 1d. Here we write A plus n minus 2d. Here we write A plus n minus 3d, etc. All the way down to, what's this? This is the first term, so that's just A, and this is the second term, that's just A plus D. And this all adds up to the same thing, of course, because all we did was to write the entire thing backwards. And what's the play here? The play here is to add up this equation. Add these two equations, I should say. Okay, well, if we add them up, kind of what happens? Alright, being a little bit careful about this, we have A plus n minus 1d. Well, what is that? It's 2A plus n minus 1d. Now, we have what? A plus d and A plus n minus 2d. Alright, well, again, I have two A's. How many d's do I have? N minus 2 plus another one. So another n minus 1d. Okay, and maybe just already we're just kind of done or something, and you see where this is going, because every one of these is going to be 2A plus n minus 1d. Why? Because the logic is the same as before, but now there's a lot more variables kind of going around, so it's more confusing. But as we move along row 1, each time we add d, so add d, etc. But in the bottom row, we are subtracting d each time. And so if in any given column is always going to stay constant, because this number is going down by, this number is going up by d each time, this number is going down by d each time. Okay, so what's this? It's also 2a plus n minus 1 d, and this last one is also 2a plus n minus 1 d. And what do I get over here? Twice the thing I'm looking for. Okay, how many of these are there? There are n of them, because there are n things I'm adding. So we have n of these, and there we go. The answer to this problem, therefore, is, well, I have this expression, which is 2a plus n minus 1d. I have n of them, so I multiply by n, and what does that give me? It gives me twice the thing I want. And therefore, the thing I want is that divided by 2. Okay, so this is sort of amazing. What have we just accomplished here? We've accomplished exactly what we wanted, which is a formula that will tell me in terms of a, the first term of the sequence, d, the common difference, and n, how far out you're going in that sequence, the sum of the first n terms of that arithmetic sequence. Okay, and I'm going to put like a star here or something, because I think this is the real formula. And this is the formula you should sort of know and kind of understand. But it is also possible to write this out a little bit differently. And that's because, watch the following. Here we have n over 2. And inside this 2a plus n minus 1d, well, that kind of looks familiar, right? In fact, I might think of that as like a plus n minus 1d. In other words, and I'll maybe put like a little red line under this or something. What is, what can I, how can I sort of interpret that thing in the brackets? Well, it's just like the first term plus, what is that? It's the nth term. So there is like another kind of interpretation of this formula, which is that the sum of the first n terms in an arithmetic sequence is n over 2 times the first term, and maybe I want to write this as like a1 now, and the nth term. Okay, and this is, also a correct formula for the sum of the first n terms of an arithmetic sequence. And this is kind of, also good, I'll just say. And this sort of says something kind of deep, especially if we write it in sort of yet another slightly different form, which is to say that the sum of the first n terms is n times a1 plus an over 2. And now we think of this as saying that the sum of the first n terms of an arithmetic sequence is n times, and what's this? Well, it's like the average of the first and last term. And, well, that's very reasonable, because suppose I want to add up to, here we go, take the generic arithmetic sequence that we started with, 5 plus 8 plus 11 plus 14 plus 17, say. So this is the sum of the first 5 terms of this arithmetic sequence. Well, then if that's the case, then this first term 5 is a1. This last term 17 is like a5. And well, what does it mean to take the average of them? Well, because arithmetic sequences are so symmetric, what do? You're just adding up each time. So if you're adding up the same thing each time, then the sequence is kind of like symmetrical, right? And so the average, which, okay, in this case I'm considering an odd number of them, so the average will be sort of just the term in the middle, but it works even if there are an even number of terms. The average is just 11. But, of course, so what does the formula say? The formula says you just take the average number and you multiply by 5. Well, that's just true, right? Because the average, if I add, what am I trying to say here? I guess I'm trying to say that 8 and 14 is always like 3 more than 11, and 8 is 3 less than 11. And when I look at 5 and 17, 5 is 6 less than 11, but 17 is 6 more. And so the 5 and the 17 kind of balance each other out, and the 8 and the 14 kind of balance each other out. So you might as well think of yourself as having 5 11s here, which is kind of what this formula says, right? Take the average of the first and last term and multiply by the number of terms. Okay, so however way you like to think about this, sort of the real formula that we get, and there's even maybe like another way of doing this, but all right, we'll sort of push on. Let's do 2 example problems, and then we will stop. Okay, so I'll sort of erase everything, maybe, but the formula that we have written here, and let's just kind of do, I don't know if this is even necessary, but consider, so here's example 1 or something, consider arithmetic sequence, which is defined as follows: 5, 8, 11. Okay, and now the dots are not problematic because having told you that it's arithmetic, you don't need to guess what comes next, because the difference between 8 and 5 is 3, and the difference between 11 and 8 is 3. So that means I know what's coming. And the question is just, hey, find S sub 13. So what is the sum of the first 13 terms of this sequence? And I guess you have 2 ways to do this. You can use the formula, or you can, you can do like hashtag no formula sort of approach to life. If you just use the formula, then it's quite mindless. What is, if I want the sum of the first 13 terms, then, well, here it is, right? It's going to be 13 over 2 times twice the first term. The first term is 5, plus n minus 1, well, n is 13, so that's 12, times the common difference, which is 3. And now it's just arithmetic, right? So this is 10 and 36, so that's 46. So 13 over 2 times 46. So yeah, that's just right. So this is just 13 times 23. So whatever that is, 230 and 69, so it's 299. Okay, is there like another approach? The other approach is to just kind of do it out every single time from scratch or something. So what am I doing? I'm adding 5 plus 8 plus 11 plus, how far out do I go? To the 13th term. Well, what is the 13th term? What's a sub 13? Well, it's going to be 5 plus a bunch of 3's. How many 3's? By the time I've got to the 13th term, I've added 3 12 times. So that's 36 and 5 is 41. Okay, so that means I'm going all the way up to 41. And once I just write it like that, then I could just do it, right? So this is 41 plus going back 3 would be 38. Going back 3 more would be 35, and I just keep going back 3 until the final one would be 5 again. And I add these up. What am I going to get? I'm going to get 46. Here I get 46 also. Here I get 46 also, and I'm always going to get 46. I'm going up by 3 in the top, down by 3 in the bottom. Blah, 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 blah. That's also 46. How many 46s do I have? 13 of them. And so 46 times 13 is going to be twice the thing I want, and therefore the thing I want is 23 times 13. Okay, that was really fast. I never sort of do this in class. I've had kind of like a change of heart in recent years, because there's all these formulas, and like, yeah, you can just like learn all the formulas and derive the formulas and prove the formulas and write them down in flashcards and use them, and but it's all kind of a little bit mindless. So any reasonable person would just tell you, hey dude, learn the formula, and then doing a problem like this is just a matter of just cranking out the formula sort of mindlessly. But maybe somehow our lives are like enriched or something in some kind of deep way by just being aware of the formulas, but sort of like, intentionally, just not using them, even though they're there, and just sort of inefficiently doing the problem all over again, kind of from scratch every time, using the sort of ideas that are contained within the formulas. So I have a newfound kind of appreciation for maybe just doing it this way. So it's really just up to you. Okay, good. We're going to do one more thing. Example 2. This is sort of now a little bit harder. And okay, admittedly, this is a little bit of an artificial problem, but anyway, I like it. So example 2. This is hard enough that it's like not in your textbook, but it's really not that hard. So here is the problem. Take arithmetic sequence 3, 10, 17, 24, etc. And once again, this is not ambiguous because not ambiguous because I'm telling you it's arithmetic, so we just know that we're going up by 7 every time. And now, here it is. The sum of the first n terms, I tell you, is 279. And now the question is, find n. Okay, so in other words, find out how many terms of this sequence, how many terms are required to be added in order to produce a sum of 279. And okay, this problem was designed in advance to sort of work out, so you don't have to doubt this. It must be true that if I add up, 3 plus 10 is 13, 3 plus 10 plus 17 is 30, 3 plus 10 plus 17 plus 24 is 54, etc. If I add up enough terms, then I'll get 279. All right, this might be a good time to discuss a feature of this unit, which is that we are investigating general methods of solving these kinds of problems, and so this goes out to my own students, I suppose. If this were math team or some kind of timed competitive test or something like that, and the only thing they cared about was getting the right answer, then it would definitely be more efficient than what we're about to do. To just kind of, in a totally mindless way, with no understanding or pattern recognition or anything, just kind of crank out these numbers. I mean, just literally do what I was already doing, right? The sum of the first 4 numbers is 54, and then, what's the next one? Okay, it's 7 more than that, so it's 61, and you don't have to go out too far until you just get 279. But I would like us all to agree that is silly and ridiculous and provides no kind of enlightenment or understanding. And so I just want to say, for the next 6 weeks of this class or something, that class rule, all problems like this must be solved in some kind of algorithmic manner, which your methods should work. Even if the numbers were, astronomically larger than they were. So I've given you small numbers, so things are chill, but don't let the small numbers lead you into just trying to do the problem in a way that actually involves no reasoning or anything like that. Okay. So we're going to resist the temptation to just mindlessly add and sort of keep count or something until we get to 279. Computer scientists can do that. Let's determine the answer in some kind of logical fashion. All right. Well, here's where it's really nice to just know that formula, man. And I do know it. The sum of the first n terms is n over 2 times 2a plus n minus 1d. Let's go. What have I been told? I've been told that 279 is the sum of the first n terms, but I don't know what n is. So this is n over 2. What's a? A is 3, so this is just 6, plus n minus 1, and d is 7. And so, basically now I'm going to work backwards using algebra to find out what the n is which satisfies this equation. And this is just a quadratic equation, so this maybe shouldn't be that hard. Let's do it. 279 times 2. Yikes, that's already kind of big. Well, that's 2 less than 280. And 28 and 28 is something 56, so that's 558. Okay? So 558 equals n times 6 plus 7n minus 7. Okay? So 558 equals n times, well, that's just 7n minus 1. Okay, so 558 equals 7n squared minus n. And, alright, here we go. That wasn't too hard. 7n squared minus n minus 558 equals 0. Okay, but this isn't the kind of, this isn't the kind of quadratic equation that is necessarily so easy to solve, because these numbers are like huge. How should I solve this? You might be tempted to like reach for a calculator or the quadratic formula or something like that, but no, I don't need the quadratic formula because the solution to this problem is an integer, right? N has to be a natural number. N is like 10 or something. So if n has to be a natural number, then it means that one of my solutions to this problem is just an integer. It's a rational number. And so, if one of my solutions to a quadratic equation is a rational number, then the other one must be a rational number as well, because irrational roots come in pairs. Therefore, what I'm trying to say is this factors. So if you know that this factors, and we do know that it factors, assuming that the question was written correctly, then it always pays to just factor it instead of trying to use the quadratic formula, especially if I don't have any technology on me. Alright, well, how are we going to factor this? Fortunately we have like a method. The method is, to write the factor pairs of 7, kind of in both ways, and now we need all the factors of 558. Alright, so if you didn't learn this in middle school or in 9th grade, let's do it now. Let's just perform a complete analysis on the number 558. We will make a factor tree. Hopefully Kirk taught this to you. What goes into 558? 2 certainly does. How many times does it go in? Well, we've already seen 279. Alright, well, does 279 have any special property? The sum of the digits is 18, which means it's a multiple of 3. So how many times does 3 go in to 279? In fact, maybe you want to be even more smooth and say that 9 goes in, because the sum of the digits is a multiple of 9. That's another kind of rule. And that is in fact going to go in 31 times. Because 9 goes into 270 30 times, and 9 goes into 9 once. And then, of course, 9 is 3 times 3. But 31 is prime. And so, I'm done. And by I'm done, I mean I have produced the tree whose leaves are 2, 3, 3, 31, which is just another way of saying I've produced the prime factorization of 558 is 2 times 3 squared times 31. And therefore, when it comes to listing all the factor pairs of 558, I can do this in a very deliberate way. What's the way? Well, 558, 1 is a possibility. That seems kind of unlikely. 279, 2 is a possibility. That seems unlikely. What's the next biggest one? Well, 3. And if I grab 1 3, then what's left over? 2 times 3 times 31. So 6 times 31, so that's 186. I think I did that right. 6 times, what did I say? 6 times 31, yeah, 186. Well, what's the next option? Well, 6 is an option. If 6, then 93. Okay, what's another option? 9 is an option. If 9, then 2 times 31, which is 68. And then I think the only other option is, right, I grab a 2, I grab a 3, just a 3, I grab a 2 and a 3, I grab a 3 and a 3, I grab a 2, 3, and 3. So that's 1831. So that is a way of producing all possible factors of some very big number like 558. All right, and now I'm looking for products whose difference is -1. So I can look at just the ones that. So let's just do it. How do I do this again? Let's see. There it is. 9 times. No, I changed my mind. What just happened? 1. 18, no, that doesn't work. Oh man, 9 times 7. Did I mess this up? 9 times, I did mess this up. 2 times 31 is 62. Okay, so that was the one I wanted. Because 9 times 7 is 63 and 62. So alright, there it is. This is just kind of remedial practice with extremely difficult Algebra 1 problems with huge numbers. But look, we handled it. The factorization of this is 7n squared minus 63 plus 62. And therefore the solution to this quadratic equation is -62 over 7 and 9. Of course, in the context of this problem, this is garbage, and therefore the answer to this problem is that n equals 9. 9 terms are required to get a sum of 279. Okay, that is it. That is your introduction to arithmetic sequences, and I'll see you guys next week. See how long was that? Yeah.